Germans aren't funny, so sorry about that. So welcome to our presentation. I'm glad to see you all here again. We would like to talk about our latest collaboration, Matt and I. So we've been tinkering since last year on this project pretty much. If you have seen Lord of the Rings, or if you have read the books even, then maybe you catch this tongue-in-cheek subtitle here, one card to rule them all. Just to be sure, I'm not referring to all the fine products that are being sold here. I'm just talking about the stuff that I've been tinkering with since joining Tandy Assembly here. So namely TRS-IO and Pocket TRS. But basically the agenda for today is I want to just quickly recap on how we got here, then followed by a high-level overview of TRS-IO++. Some people already asked me why the plus. Well, I was once interviewed by Björn Straustrup, so I've gotten a liking to the plus, so that's where that came from. A lot of slides on some internal details, and then at the end we'll do a demo.
Before you move on, Arno, mention one thing. So anybody that's familiar with technical literature knows that whoever's name is listed last did the most work. So you typically would have the professor and his student.
Yeah,
but
no.
Just so don't be fooled.
Don't believe him. Don't believe him. So I just want to quickly run through the history of also my journey in this community here. So Sasha and I, sitting in the audience here, we basically joined almost every single Tandy assembly starting in 2017, and our first entry was to purely on the software side. So we've been tinkering with an emulator for Android. If you have an Android phone, you can still find it in the Google Play Store. You can look for TRS-80 and find our emulator. But what we demoed back in 2017 was basically what we called the retro store. So kind of giving you the same seamless way of downloading these old apps onto your phone than what you're used to from those modern app stores. So we did that purely on the software side. So Sasha implemented the cloud service, and he also tinkered with on the emulator side. But basically that was just purely on the software side back in 2017. Someone said, well, wouldn't that be great to also run on a real machine? So basically have the RetroStore client run on a real machine. So next year, 2018, then we came back here with the first piece of hardware I ever designed, the RetroStore card. And I can tell you my thing in this community is not to collect, but I like to learn new stuff. So you can probably see that the PCB was not laid out very nicely. So I used actually a tool called fritzing. It had like an auto layout feature, which I was very grateful for, being the first time trying to do this here. But I got some not so kind notes, feedback on the traces going like wiggly all the way over. But anyways, it was my first entry. It had an ESP32 microcontroller, had a GAL, the same one that Ruth mentioned this morning, and it connected to a Model 3. So, but it was only tuned towards the RetroStore application. Then someone said, well, how about adding thread functionality to it? So okay, why not? And then I did that, and the result was this. And actually I collaborated back then with Andrew Quinn from New Zealand. And you can see it's a lot more professionally designed. I also then, he did this, but he told me about KiCad, and I also then picked that up. It had the same components, but it also was able to support Fred. So it had the RetroStore functionality, but also it gave you all of the Fred functionality. So that was back in 2019 for the Model 3. Then Tim Helleran said, well, how about if you try to also do that for the Model 1? So I didn't have a Model 1, and he was kind enough to give me one of his Model 1s. And then, oh, sorry, so I forgot. So the latest version of TRS-IO for the Model 3, where we replaced the GAL with an FPGA. It also gave us some extra functionality. So here you have the ESP on the far left. Far right from your perspective, and then next to it was the Tang Nano 9K. So a very nice, pretty cheap FPGA. And we also switched to surface-mounted computing, so you can actually components. You can actually see the development also on my learning experience with a soldering iron and being able to solder these things. So that's the latest and greatest we have on the Model 3. Model 1, that coming back to the story, so Tim, thanks for your Model 1, and that was the first version of the TRS-IO card for Model 1. You can see on the bottom the 32 SRAM module that gave up to 30 kilobyte for the Model 1, but basically the same thing. It was had a 40-pin connector, and that was back in 2021. So we also gave that a facelift, replacing the GAL and the SRAM with the same FPGA. So the FPGA can also then serve the upper 32 kilobyte. So that's the latest version that exists right now for the Model 1. So having come here several times, I realized flying in from California that it's not really practical to bring any gear. So then I thought, well, how about if I do something like PocketTris? So kind of like recreating the old machine using modern components. And that was actually then the breadboard version of the early version of PocketTris. And here again, Andrew Quinn helped me then with the layout of designing a modern board. And it basically has again this ESP32 microcontroller, but the expansion interface on the bottom, or the edge card connector, now is kind of flipped in functionality. So for TRS-IO, you connect it to a vintage TRS-80. For PocketTris, you can connect vintage peripherals like a hard disk. And actually last year we demoed this. Matt brought one of his hard disks, and we showed how PocketTris can boot off one of those vintage hard disks. It had a VGA connector on the top. It had a PS2 card. It is still in existence. I mean, it still is around, and there were quite a few people who also built it up. So a little bit tongue-in-cheek here again. So that was a birthday cake, and you can guess that my friends made for me. And Sasha, were you involved in that one? No? Okay. But you can tell the year from the wiggly lines that was actually then 2017, my birthday, because they took the old RetroStore card as the base kind of. But I really love this. I mean, just the level of detail, even at like the MOSFETs on the far left and the ESP on the top. Very nice job. So anyway, so then last year when we kind of discussed what to do then next, that is where the idea came for TRS-IO++. Because when you think about the hardware, when you looked at the PCBs, they look similar when you look on the top level. Right? You had these edge connectors, but they worked in different ways. Either you connected to a model to a TRS-80, or you connected vintage hardware to it. So then the idea of TRS-IO++ is just like the tagline says, one card to rule them all, is to build a PCB that can be used in both ways. You can basically, with a little dip switch, you can tell it, okay, now you work as a TRS-IO card, and I connect you to the TRS-80, or you wiggle the dip switches and tell it, now you're going to be a PocketTris, and I can attach vintage hardware to you. So from a TRS-IO perspective, TRS-IO++ is just simply a combination of both the Model 1 and Model 3 functionality. So what is a little bit more interesting is to compare for PocketTris and TRS-IO++. So this slide here, the table, kind of discusses or talks about the difference between the original PocketTris card that I just showed and the TRS-IO++ card. And for emulation, PocketTris could only do Model 3, Model 4. So it didn't have any Model 1 or Model 4P. So Matt then also added this for TRS-IO++, and he will talk about that extensively. Then he has some slides about this. PocketTris used VGA. TRS-IO++ is using HDMI. They can also be used for sound. So if you connect it to HDMI, you can also actually get sound of it. Graphics, PocketTris only supported graphics, and then TRS-IO++ has a whole bunch of different graphic standards that it supports. Sound, PocketTris was limited to simple cassette sound, but it did have like a 3.5 millimeters audio jack that you can connect to your stereo. TRS-IO also has that, so it emits sounds on the 3.5 audio jack, but it also does it on the HDMI signal. But Matt also included orchestra support. Cassette in, that was one thing I was very proud of for PocketTris. So you basically could also then use that same 3.5 millimeter audio jack to then play a cassette file that you had on your phone, and just basically get those blinking asterisks when you do C load from within the emulation. The hardware is there on TRS-IO++, but I didn't port that over yet, so that's still TBD. CPU speed, Pocket TRS was limited to barely 2 megahertz. The ESP was just completely maxed out with everything I was running on it, from creating a VGA signal, so the most you could do was about 2 megahertz emulation. TRS-IO++, the Z80 core actually runs on the FPGA, and Matt will also talk about that. So here it's, 4 megahertz, no problem, and you can even go higher. Pocket TRS had a little configuration screen. Those of you who had Pocket TRS cards, you know you could hit F5 and you got into a configuration screen. We also show that later. So that is also supported by TRS-IO++. Both Pocket TRS and TRS-IO++ have an internal TRS-IO card. So you don't need to connect an external, but the ESP that is on the PCB can also is running TRS-IO. So you have everything basically packaged into one. Yeah, and finally, expansion interface. The Pocket TRS only mimicked Model 3, Model 4, so it had the 50-pin connector, edge connector, and TRS-IO++, as you will see shortly on then the PCB view, then has both a 40-pin and a 50-pin edge connector.
Just me? Hi. So as Arno mentioned, so the TRS-IO++ combines the ESP32 with an FPGA. So we have kind of a software-intensive component and a hardware-intensive component. So in the original Pocket TRS design, where the full TRS-IO was emulated in software, we can now emulate it in hardware. So in this new architecture, we really have the TRS-IO part doing what it originally did. It's back to a pure software component emulating only the TRS-IO functionality, and then we have the FPGA that's able to implement the hardware component, the TRS-IO itself, in hardware. So in TRS-IO mode, the FPGA isn't really doing a whole lot. It varies depending on whether it's a Model 1 or Model 3. On Model 1, we emulate the upper 32K, but besides that, it's not really doing a whole lot of hardware. I guess the high resolution graphics as well, but it's not very hardware intensive. When we do the Pocket TRS mode, now we're emulating the full TRS-80 as well as any additional features like the graphics or whatever. My involvement has been mostly on the FPGA side. I was doing my own implementation of, Arno had called it an XTRS. So I was doing my own implementation, and then when he decided to do this, it was natural for us to collaborate on this development. So most of what I talk about is going to be regarding the FPGA implementation. And then Arno, if you want to jump in on anything about the software and ESP32, feel free. So we have these two distinct modes. The TRS-IO mode is where we're emulating really the TRS-IO functionality. And in principle, it behaves, as Arno said, just like the two individual TRS-IO boards, the Model 1 and the Model 3, but the one board can do both. So it does all the TRS-IO functions as before. It does Model 1 screen mirroring. So if you connect it to a Model 1, you can get screen output through the HDMI, which is a nice feature. But the TRS-IO Model 1 also does that. We get high-res graphics. For the Model 1, we use LE18, if you're familiar with those, low electronics 18. And for the Model 3 and Model 4, we either do Tandy or the graphics solution, so aftermarket. Orchestra 8590, I don't really even know the difference. I think 85 is just the Model 1 peripheral, and Orchestra 90 is the Model 3. But they have different I/O addresses, but otherwise I think they're the same functionality. And one of the interesting features is that there's something called a PMOD interface, which is a kind of a de facto standard on FPGA development boards for connecting additional peripherals. So you can get some standard, a lot of different standard PMOD type peripherals, and then you can build your own. So it gives you, some expansion capability, provides some interesting capabilities. So the Pocket TRS mode is really the mode that I've been most involved with. And we implement the Model 1, the Model 3, the Model 4, and the Model 4P. And we have a Z80 soft core that we use for that. And that's actually taken from the MR project. I think it's the MR project, which is another emulation project. There's a bunch of Z80 cores out there. Not all of them are psycho-accurate. When I first got into this, I didn't realize how important psychoaccuracy was. But the more you get into it, the more you realize that if you want to emulate the machine authentically, you really need to have a psychoaccurate core. I went through probably about 4 or 5 cores before settling on this one. It can connect to real TRS-IO peripherals. It has an internal TRS-IO which can be disabled if you want to use an external TRS-IO or a real FRED. And then it has the additional features, again, high resolution graphics, orchestrating, 8590, and a PMOD expansion connector. So this is just a block diagram of what the TRS-IO++ board looks like. But go ahead to the next slide, and you'll see an actual. Oops. Oh, some we got out of order. Oh, there we go. Okay. So this is the actual board. So in the middle we have the FPGA, which is a SIPI Tang Nano 20K. So 20K means about 20,000 logic elements. Has some additional features, internal RAM, and so on. This is the PMOD connector. The TRS-IO has traditionally had an RGB LED, which is located here. That's the cassette in and out connector. We have the HDMI connector, the keyboard. We've got some push buttons, SD card socket, the ESP32, and then we have the 2 expansion connectors at the top, both the headers and the cartridge connectors. And most of the ICs you see, the 3 up here, and there are actually 2 that are hidden under the FPGA module. Those are just level translators. The FPGA is predominantly 3.3 volt, and we need to interface with 5 volt devices. So that's really about it. It's almost literally a 2-chip solution in connectors. If the FPGA and the ESP32 were 5 volt compatible, you wouldn't really need anything else. All right, next. So this is the circuit board. I don't know why I'm talking to this, because this is really all Arno. He did the circuit board. I did some review and refinement, improved some of the grounding. But this is the Model 3 connector at the top, Model 3 4P, and that's the Model 1 connector. So one of the interesting things about it is the arrangement of the Model 3 interface is much more regular. You can see the lines very uniform. We're on the Model 1 side. You can see that they're just all scattered. There's really no particular organization to it. Very poor grounding. And without really quite a bit of the work that I did was trying to improve the grounding on the Model 1 connector, because the biggest problem, in my opinion, with the Model 1 is the real Model 1 is noise. So you can see here's the FPGA socket connector. That's a SDRAM type connector, right? What's the name of that connector? The socket? The DDR3. So it's a DDR3 form factor. The ESP32 and then various components scattered about. Next. So this is Arno again.
It's me. So I wanted to talk about the interaction between the ESP and the FPGA. And actually a lot of that already I was basically adopted from TRS-IO, because it almost is identical with TRS-IO. So ESP and FPGA, they communicate via SPI protocol, where the ESP is the primary and FPGA is the secondary. So it has the usual MISO-MOSI, I don't know how you pronounce it in English, line. So the first arrow is actually 4 different lines. Then there's a line request where the FPGA can asynchronously notify the ESP that something needs to be done. So for example, when the FPGA sees that there is a FRED command or retrostore command, then the FPGA can ping the ESP with a request line. Then there are 4 lines S0 to S3 where the FPGA can give like what's happened. So the request basically says something happened, and then the ESP can then inspect those 4 bits and figure out what actually did happen. And on the table on the right, you can see then different values. So for example, if S0 to S3 are 0, it means that TRS-IO did an in command on port 31. If it's 3, it means that the FRED, that the computer tried to do an out on port C X. The ESP can signal that it's done whatever it had to do with the done line that is going back again. I dedicated a separate line to that to be a little bit faster. I did not want to do like an SPI command going down. That would have been a little bit too slow. So just one additional line, and I can tell the FPGA, okay, you can continue. And then actually, up until now, this is identical with TRS-IO. So if you look at the schematics for TRS-IO, both for Model 1, Model 3, you will see all these connections between the ESP and the FPGA. What is new in TRS-IO++ is also then the connection for the JTAG interface. And we'll talk about that a little bit later, but the ESP is able to update the FPGA at runtime. And there's a reason for that that Matt will also mention, but that is something that the ESP can also do. So you don't need to have a programmer to flash the FPGA, but actually the ESP can do that. So in the next slides, I have the SPI commands. There are by now 27 different SPI commands that the ESP can send to the FPGA, and I'm just going to point out a couple. So the first one, get cookie. Well, that is the FPGA can, the ESP can see if the FPGA is actually there. So when the ESP boots up, it requests a cookie and it makes sure it actually can communicate with the FPGA. A very common thing. Let me just see what else is here. So there's one here called set screen color. So on TRS-IO++, you saw that there is an HDMI output. So actually the FPGA is creating the HDMI signal. And in order to support the three screen colors, green, amber, and white, the ESP tells the FPGA what color it should do, and that is done by an SPI command. It's called set screen color. There's another one on the bottom here, send keyboard. So the PS2 keyboard is connected to the ESP and not to the FPGA. And the reason I did that is because the ESP is easier to handle different locales. You have a different keyboard layouts, German, American layout. It's easier to handle in software on the ESP than rather try to do that on the FPGA side. Just to give you an idea on all the different kinds of this interface, so it's gotten pretty complex now with 27 different, here's some more. So there are also a whole bunch of things where the ESP can tell Pocketress running in quotes on the FPGA to stop and resume. So these are all new commands for added to TRS-IO++. I wanted to talk about, so the original Pocketress, so if you ever had a Pocketress card, you could hit F5 on the keyboard and it would scroll in a configuration screen that was part of Pocketress, where you could set things like screen color, or if you want to disable the internal TRS-IO, or what kind of ROM you want to enable. And I wanted to add this also to TRS-IO++. Now, on Pocketress, everything is in software, and everything runs on the ESP. So intercepting F5 and then doing the thing, stopping the Z80 emulation and then scrolling in that screen, that was all pretty easy to do. Now on TRS-IO++, because the actual emulation of the Z80 core is running on the FPGA, there is now a split. So you have the FPGA that is running the Z80 core, and the Pocketress user interface, the configuration interface, still runs on the ESP. So I just wanted to show how this ping pong game works then in TRS-IO++. So if you hit F5 under TRS-IO++, the ESP intercepts that. And then it will send via SPI the Z80 pause command so that the Z80 core on the FPGA stops running. Then the ESP reads the current display content via some other SPI commands. So basically it reads out the current content of display memory and stores it inside the a mallocked memory region on the ESP. Then I use TRSLib, another project of mine, to then build up the user interface for Pocketress user interface. And then I use, again, SPI commands to just simply scroll it in from the side. And what is kind of I was a bit surprised. Actually doing that via SPI was fast enough. So I have a simple peek-poke interface from the ESP to basically manually meddle with the FPGA's display memory. And it's again hooked up to SPI, but we use that to then create that same scrolling, left scrolling effect that you may have seen on the original Pocketress. Well, in that case, once that happens, then the Z80 core is paused and the whole user interface thing happens then on the ESP side. then when you hit escape and you exit the configuration screen, then the same thing happens in reverse. So we just take the saved background buffer and scroll that in from the right. And then last but not least, then I tell the Z80 core, okay, resume running, and then it just continues where it left off. Or it continues where you stopped it. So it kind of shows that for TRS-IO++, this interaction between the ESP side and the FPGA side are a little bit more complex. But it gives you the same effect. I'm going to demo that later.
Oh, here we go. So regarding the FPGA selection, good questions. Why the Tang Primer 20K? So one of the big reasons really was just availability. A year ago, it was almost impossible to get FPGAs. Xilinx, Altera, they're just unobtainium. But these were still available, very cheap, about $20 for that part in module form. Large I/O count, that was one of the big limitations. A lot of the easy-to-use FPGA modules were fairly low pin count. And for this application, we needed a fairly high pin count. So this is rather convenient to have about 100 pins. Relatively high density, relatively easy to use. It had onboard power supplies. It has onboard JTAG, which is convenient, and the JTAG also includes a serial port. We currently don't use it in this design, but there's a chance we would in the future, but it is a nice feature. The one kind of significant downside is that it's a DDR form factor, which is somewhat hard to solder by hand. You wouldn't want to learn on this board. So next.
Let me just say it's impossible to solder. I screwed up like 3 boards trying to do it. Matt soldered 2 of them, so he's the soldering god. So if you have any questions about techniques to do that, ask Matt.
Yeah, it is all technique though, but
it's in the list. But.
Yeah. All right, next slide. This gives you kind of a rundown of what the FPGA resources look like. So FPGAs, obviously they have logic gates. That's what most people think of FPGAs as. But they typically have other dedicated resources. RAMs, of course flip-flops, PLLs, clock generators, GPIO. DSP is kind of a DSP block. It typically is some kind of a multiply accumulate block. We don't use any of those currently. This particular module has a 1 gigabit SDRAM, which would seem potentially rather nice, but modern SDRAM is fairly difficult to use. We might be able to work it in a design in the future, I don't know, but it's not, modern DRAM is not like the DRAM that you might be used to, where it's really random access. It's more transaction based. It's kind of intended to be behind an SDRAM controller, with some type of like a cache interface. It doesn't hook up to a Z80 very easily. So at the moment, we're currently not using it. So BRAM stands for block RAM, and in the FPGA, it can be either a single port RAM, a dual port RAM, or it can emulate ROM. So for this design, the BRAM was really the limiting element. We have plenty of logic, plenty of other resources, but the limited BRAM pretty much drives almost all of the design decisions. And you'll kind of see that a little bit clearer in a few slides. But just for example, this part has 92K of block RAM, and you're not going to get 128K Model 4 with 92K of block RAM. So, next. So this gives you a breakdown of really the BRAM utilization for TRS-IO mode. So TRS-IO mode is not going to be the more demanding one. So in this case, you're going to find that we have plenty of block RAM. So we kind of look at some of the features, the block RAMs they require, and oh, no, I'm sorry. This is the feature list. Sorry, the next slide. So this gives you a breakdown of what the features are, and then we'll look at what the block RAM utilization is. So we have the multiple machine modes, and we have the multiple features, and indicates whether or not they're implemented in that particular one. And I think Arno went over this earlier, but we have all the TRS-IO features, including Fred, and that's of course implemented with all of them. We have the text screen for the Model 1 via bus snooping. We still support the CRT, text mode only. And then we have the cassette sound, we have orchestra sound, we have high resolution graphics of one form or another. the one limitation is on the Model 4, the high-resolution graphics board is internal, and we connect to the external bus. So we can't fully emulate, at least not conveniently emulate the Model 4 graphics. But we can do it kind of Model 3 style, where we're completely external, connected to the external bus. And then with the keyboard, we can also use the Pocket TRS keyboard connector to replace the keyboard on the machines. On the Model 1, you would have to disable the internal keyboard. On the Model 3 and Model 4, we could make actually a little PMOD adapter that would allow you to do that. All right, next, Arno. So I think this is the slide I was talking about. Yeah, so this is the one now that really indicates the amount of block RAM utilization for the various features. So in TRS-IO mode, we're using the real machine, so we don't really need any ROM, but the Model 1 has only 12K ROM, and a common enhancement is to add a 2K ROM in the 2K open area. So we could implement 2K of ROM there, and that would take 1 BRAM. We implement the external 32K, the upper 32K RAM. We do the display mirroring, and that requires the character generator ROM, which is 1 BRAM. We have the high resolution graphics. For the LE18 graphics, it's only 16K. For the other graphics, we have enough memory that we can implement the full Tandy, which is 32K. So the total BRAM, you can see the column 26, 27, 16. So we have plenty of BRAM, right? There's 42 total, so we're plenty. And so the slack is the extra. So a positive slack means you have enough, a negative slack means you don't. We still need the 1K of display RAM, even for the Model 3, 4, and 4P, because we still would implement the configuration screen. So even though we can't implement the TRS-80 screen, we still need to have that. And as I mentioned, we can't do the true Model 4 graphics because we just don't connect to the appropriate point within the machine. All right, next. So then this is going to be the PTRS mode. So this shows you all the BRAM utilization. So here we're emulating the full TRS-80. So we need the full ROM, we need the full RAM, the display, the character generator because we have to generate the display, the high resolution graphics. Without going into too much detail, of course we have the ROM, which is typically 12K or 14K. The interesting thing is on the 4P, it's only 4K. There's only a 4K boot ROM on the 4P. So we have RAM, 48, 64, 128K. The display is 1K or 2K for the Model 4. Character generator ROM, we need 1 VRAM for that. High resolution graphics. The graphic solutions high resolution board is only 20K. So if you look at the totals, you see that in a couple of cases we're negative. We have negative slack, which means we don't have enough memory to implement those things. So the interesting thing is, and certainly we can't do the 128K, but the interesting thing is when we look at the Model 4, we're 5 VRAM short. So we can't do high resolution graphics. But interestingly enough, if we emulate the Model 4P, we reclaim 10K from the ROM, which gives us just enough memory to do the high resolution graphics. So that's really the main reason that we chose to emulate the 4P. There's almost no real reason to. You could do everything with the 4, except we couldn't get graphics. So you can kind of see that if you want to do high resolution graphics at the moment, you have to emulate the 4P. I don't know if there's any particular reason to emulate the 4 over the 4P. It's a little bit clumsy. I don't know if everybody's familiar with the 4P, but I had never worked with the 4P before, so it was kind of interesting to me to get to learn a little bit more about it and some of the kind of the quirks about how it boots. So next. Ideally, we would have one design that would cover all modes and all machine modes. But that's really very difficult because of the limited VRAM. So the easy way to do it would be you would just allocate your resources wherever you need them, and then you would use them or not use them. You could put 20K or 32K in the high res board, and if you were using the graphic solution mode, you just wouldn't utilize the other 12K. But we don't have the luxury to do that. We're really limited with memory. So it's if you have enough resources, you just switch things in and out. In this case, in order to do it, we would have to like move the BRAMs around, which becomes very difficult because it's like, here it might be, a 14K ROM. If we want to switch to a different mode, we have to break it in half, and 10K goes here, 4K goes here, and that becomes rather tricky and clumsy. So, so I just decided we're just going to do, multiple modes of operation. And so that's where the loading of the program comes in. So with the ESP able to load the FPGA program, it's not so terribly clumsy. You don't have to get your programmer out and do it. You just select the mode with the dip switches, it loads it up, and boom, you're up and running. So as I said, it can load the FPGA firmware. And another note is the ESP firmware, though, is the same for all modes. So we don't have to, that would be inconvenient to program because that takes several minutes. It's in Flash. So we run one ESP firmware and 5 FPGA firmwares.
Okay, so just some quick comments. Like as Matt mentioned, we decided not to have like one common design. It's just maybe it might be possible.
Yeah,
but
it was his goal, but not really mine.
I was hoping we could accomplish that, like one Verilog design that covers all different modes, but it was just not feasible. So we decided then, okay, as Matt mentioned, to have just one Verilog version for a particular mode. So, which also means that if you switch modes, then you have the ESP has to then update the FPGA. And that is one thing that I then also contributed. So using JTAG, there's a way. So JTAG, I knew it only as an acronym, and I learned a lot more than I ever planned to learn about it. But you can do a lot with JTAG. And one of those things is that you can also upload then bit streams to the FPGA. So then with the documentation mentioned on the bottom, that is then how I managed to reverse engineer it and how that happens. But basically the way you do that is you with the dip switches, you say what mode you want, and then either you power cycle or you long press one of the buttons on the board, and then the ESP is using the SPI interface to retrieve the buttons that are connected to the FPGA, and then it opens the bit stream. The bit streams are stored on the ESP's internal flash. So you don't need an SD card or anything. They're actually on the ESP's internal flash, and it uploads it. It takes about 20 seconds to upload, so it's a little bit inconvenient, but okay, 20 seconds. Yeah, and that's that. So one bit stream is about 880K, so which also means we need an ESP version that has enough internal flash memory. But there are some 16 megabyte versions that are easily that can cover this.
Okay, so this is just kind of an interesting observation. So we have the 2 expansion connectors. So in TRS-IO mode, you would normally connect to one of those, depending whether you're Model 3 or Model 4, and that leaves the other connector open. So you can actually utilize the second connector to connect other devices. So in TRS-IO mode, Model 3, 4, 4P mode, you could use there must be a typo. Yeah, I know. I'm confused what I'm saying there. But in any case, you have the 2 connectors. And so the idea is if you're connected to a real TRS-IO, you're using the Model 3 connector, and the Model 4 connector is open. So you could, in principle, connect some other device there. And the same way, if you're connected to Model 1, you could potentially connect a Model 3 peripheral. So for example, you could connect to the Model 1, and you could connect a real Fred using the Model 3 connector. So you wouldn't need any kind of an adapter, like a Quinterface or something like that. You could connect it directly. And then the same is true in the other direction, where if you're emulating in Pocket TRS mode, you're emulating the full machine, then you have both connectors available. And the natural thing to do, if you're emulating a Model 1, you would connect a Model 1 peripheral to the Model 1 expansion. Or if you're emulating a Model 3, 4, 4P, you would connect to that connector. So you always have one connector that's open. So, so go to the next slide. So one of the Good, next slide, yeah. So one of the possibilities is, I mentioned how we're limited by the amount of memory. So even though we've got this large SD RAM here, I'm not sure we can make use of it. But one possible solution to that is that we could connect a 64K or 128K RAM to the Model 1 expansion interface, this expansion connector, because it's essentially the Z80 pinout. So we could connect it there, and that would free up the B RAM that's in here, the block RAM, so we could look at some other features. We could get a full 128K Model 4 machine, some things like that. So that's something I'm going to investigate. I haven't really explored it yet, but I think that's possible. Next. Yeah, so as I mentioned, one of the features is that we have this PMOD connector. And the PMOD, it's a kind of a pseudo de facto standard for FPGA modules. And it's real simple. It's power ground and 4 GPIO pins. But it comes in kind of 4 different flavors. You get a single, a 2X, or a 4X. So a single is just a 6-pin single row header. The 2X is a double row, so you get 8 GPIOs, and the power and ground are redundant. And then the 4X is where they take 2 of those, put them side by side with a standard spacing, and then you can plug in even bigger devices. So TRS-IO++ has a single PMOD connector, but it provides a lot of possibilities. You can go to the Digilent website, and they've got pages of standard PMOD peripherals. You can get little Wi-Fi boards, you can get VGA adapters, you can get a full ESP32 board. It's really quite a few. You get PS2 connectors, all sorts of things. So it's a kind of a rather flexible interface that we can start connecting other things to. Or you can do custom PMOD adapters, and one of the ones that we'll demonstrate is the LightBright 80. And I had already mentioned that I think we can do like a Model 344P keyboard replacement with a custom PMOD. We can put additional LEDs or switches on there, really whatever you can think of. So next. I think that's really the end. I had actually planned on doing a kind of a little bit of a technical deep dive into the sound implementation of TRS-IO++. Unfortunately, I ran out of time, I ran out of energy, so I didn't really finish it. But it's an interesting aspect of the design. I'm a DSP engineer by profession, so that's probably the more interesting part of this for me. So if you have any interest in the sound implementation, feel free to ask, or just feel free to stop by our table next 2 days. So that's it, except for the demo. Ready? All right.
So we have also an exhibition table at the far end, and you can take a look at this in action.
Yeah, so currently I'm just loading up the, so I'm going to demonstrate just the PTRS mode, just because it's easier, it requires less hardware. I don't want to have to drag a Model 1 up here and cross my fingers it all works. So this is much more stable and much simpler to demonstrate. So currently we have the Model 4P design loaded up. And that's mostly because it's going to be the most flexible. I can demonstrate high resolution graphics and pretty much everything except Model 1 specific features. So one of my favorite demos is TRSVid. I don't know if you're familiar with that, but it's a program by George Phillips, and it's pretty impressive. But it's a video player. He actually presented it at Tandy Assembly a few years ago. But it's a rather impressive piece of work, given the very modest platform. But I have a hard time seeing the screen. But we can play a video. No, we're going to turn it down a little bit. There's a bunch of music videos on here as well. This is actually one that he distributes with TRS-IO, or with TRSVid. Actually, the sound on this video is not actually that good. Some of the ones I have are better. But I can, there's always a high def noise in there. I wanted to play that. So what I just did is, as I mentioned, the sound was one of the more interesting aspects of the design. And so the original implementation of sound sounded like that noisier version you just heard. And without going into a lot of detail, that was one of the things that was kind of interesting because it was an unexpected result. And it turns out it's because the way that he generates the sound, he uses PWM, we resample that to go through the HDMI, and that resampling, if you're familiar with discrete time processing, results in aliasing. So what you're hearing is that aliasing. So by filtering it prior to the resampling, then you filter off all those components that would alias and generate that sound. So that's why you can hear it. I'll do that one more time. So all I'm doing in that case is just switching a filter in and out. And obviously the cleaned up version is with filter in. Okay. No, just, oops. So this is interesting. I'll show you something else I discovered. So I'm going to try to run Orchestra 90, but it's going to reboot. The reason that reboots is, and I don't know why, but when the program starts up, it looks for itself on the disk. So Orchestra 90 looks for Orchestra 90, but it's case sensitive. So if you type it in lowercase, it looks for the file in lowercase and doesn't find it, and it reboots. But of course, the first time it happens, you don't know that. And you wonder, okay, what went wrong? And that turns out that's all that it is. Oops. Oops. Let's type something wrong. Okay, so we'll try Orchestra 90. No. Graphics. Let's try one of those.
So the sound is both on HDMI and also on the 3.5 audio jack. So
yeah, so on the audio jack, we mix the Orchestra 8590 sound is stereo, and on the cassette jack, we mix it down to mono. And again, that's another interesting aspect, because how do you produce, this turns out to be 8-bit linear PCM audio. How do you output that from a single bit, cassette port?
If it's just a single bit, can't you attach it directly to the speaker, actually, right? Because I've done that before at the FPGA, where I just take literally an output pin and hook it directly to the speaker.
Well, that is what's happening, except the input is 8-bit audio. So how do you
get it down?
Yeah, so you do it with a noise shaping or noise shaper. Let's see. So each. Oops. I type it wrong. Looks like I did. Maybe it's not on this one. Read it this way. Okay. Oh, maybe. Oh, I thought it was. There we go. So on the Model 3 or Model 4, you can mix the graphics and the text, and you can control that. And I just automatically mix them because that way I can still see what I'm typing. So I can then clear the screen so you can see the. Anyway, so yeah. So that's an example of high res. And let's try one more. Let's do, if we can find a game here. Okay, so on the game, so this is the normal Fred image. So by default, it enables high speed mode because it's a Model 4, so they typically will run the Model 3 in 4 megahertz mode. So games typically run at 2 megahertz. So let's slow it down to 2 megahertz, and then we'll do, we can do Galaxy Invader. Oops. So, I assume this is everybody's favorite game. What's that? Oh, I should have, yeah. So Arno wants to demonstrate the setup screen. So there's a setup screen they talked about. So as he said, whenever you hit the F5 key, the ESP32 actually issues a bus request to the Z80, which then stops the Z80. It issues a bus acknowledge back to the ESP32 so that it knows it has the bus, and then it's able to access the video memory directly. And then he copies out the memory, he then scrolls his screen in, and then when he's done, he scrolls the Z80 screen back, or TRS-80 screen back. So we can do configure. So there's a couple of different things we can do. We can select the ROM. We can select whether the internal TRS-IO is enabled. In this case, it's actually disabled by hardware, so it's ignoring that. But here's the screen colors. So we can select that one, go back. Now we have green screen. Or we can do amber. There's amber. So another thing we can do is we can select different ROM images. So currently, well, this isn't showing the one that's loaded. These are the ones that we have available to load. The one that's in there currently is the Model 4 P boot ROM. So we don't really have enough memory to load any of the other ones. But I have several available. I can demo it later. But if you're familiar with the XROM, one of the ROMs that we have in there is the XROM. So we can actually, we should be able to boot directly from hard disk, even with the 4P. So maybe I don't have it on the SD card. But anyway, so those are the few of the setup things that we have available currently. You can select whether or not the internal TRS-IO is enabled. You can select which ROM image to load. And you can select the screen color. And these other things aren't implemented yet, I don't think. But these are just, I think, more or less carryover from the TRS-IO, the old TRS-IO implementation. So that's all I have for the demo.
Yeah, I think that's it. Any questions? Stunned silence.
Is this available now?
That might be a limited edition, but the DDR3 connector, that's a bitch, that's.
Yeah, I mean,
we have actually played with some techniques on using PCB stencils to apply solder paste in a reflow oven. Sasha actually printed a little negative pressure box that can pull the PCB stencil down, and I hope that I have a bit more success. Like I said, I ruined 3 boards trying to hand solder it, and I cannot do it without a reflow oven. So there might be a few boards at some point, but don't hold your breath.
Have you thought about integrating the ESP32 functionality into just a larger FPGA that comes with bigger block RAMs and so forth? Because that would potentially, you know, if you went with like an evaluation board that was like more standard off the shelf, then the only parts you'd have to implement would be like any specific card edge connector or any specific, you know, inputs that eval board doesn't have.
Well, the ESP32 is more than just a CPU that's the dual core thing. It has a lot of different I/O adapters, you know, that or the Wi-Fi module. So I think, you know, you would have to replicate quite a bit on the software side. Plus, it has 4 megabyte of PS RAM, you know. So I think that is also why the Pocketress UI that you just saw at the end, I wouldn't even think of how to replicate that in the on the FPGA side. But there's Trislip, this whole thing with the form where you can like select the color and so forth. That is all done on the ESP side, written as a C library. So I would not.
Your project also started out on ESP32, so you already have this library and all this functionality that already exists.
Yes.
That you'd have to go back and respin in slightly different form.
I think the biggest hang-up, though, is just the Wi-Fi. So this particular module is really intended for RISC-V or RISC-V, I don't know how to pronounce it. It's really intended for RISC-V development. So you know, you can implement, and in fact, they have examples with the RISC-V in it. And you know, then you would have the cache controller, and you'd be able to make use of that SD-RAM, and then I think they have execute in place from the serial flash. So I don't know what kind of performance you would get from it, and how much, you know, resources, like if it tied up a bunch of that block RAM to implement the cache and stuff, then you wouldn't have that available for the you know, the Z80 emulation, TRS-80 emulation. But and I think there already are some larger FPGAs in this family. I don't think they're available on this type of a module yet. But I think what you're saying is actually, you know, practical, except you'd have to then add something for Wi-Fi. You know, and so the ESP gives you a whole, you know, dual core processor plus Wi-Fi. So
yeah, but what it does is it separates you from that form factor that's troublesome for the hobbyist to be able to solder, right? Like that's going to be something that's going to be hard.
But if you want to have the expansion interface, you still need to build up and soldering ESP is easy. Even I can do that.
Sure.
But the DR3 connector, that's a different story.
By going to a different FPGA board that would come with it already shipped, right, already installed. So even if it was a PTA, you wouldn't have to worry about how it's attached, right?
Other questions?
So the API sort of that you were showing between the FPGA and the ESP, it seems like mostly it's the ESP requesting and the FPGA answering back. I just wondered if there's any capability to go the other direction so that the FPGA could maybe ask the ESP saying, hey, can I just use your ROM image over there, not even transfer it or something, and then free up the block RAM?
Well, you remember there was one line that said request, where the FPGA can request, send a ping to the ESP. And then you have these 4 bits where you can say, well, you know, what do you want? So yes, you could do that. I mean, when Fred, like when you connect TRS-IO++ to a real TRS-80, and it does anything on port C's X, you know, like for the hard disk port numbers, then actually it goes that route, you know. So the FPGA sees this on the I/O bus, and it sends a request to the ESP. The ESP asks, okay, what do you want? It processes the FRET, whatever you want to do, and then sends the result back to the FPGA. So there is a way of doing it the other way, but SPI is like a primary secondary protocol. You know, it's not symmetric. You know, it's asymmetric. Other questions? Okay, then thank you very much for your attention.